It might go over your head, not gonna lie, okay? But we're gonna spend much more time on this concept in the next unit. So it's okay if you don't get it like right now, because it's gonna start to kind of sink in hopefully a little later, okay? So we've been talking about improper integrals where we have some type of an infinity as a bound. And we looked at, remember P-series, or like those x to a power? We said how it all revolved around that number 1. We had a little bathroom humor, remember? Okay, so we're going to kind of revisit that a little bit today too. What we're going to do is we're going to kind of sneakily, if that's even a word, determine if an integral converges or diverges by comparing it to a different function. So maybe one integral is very difficult for us to work with. We're going to try to figure out something that it acts like, and then if we can figure out what the easier one does, then we can probably figure out what the harder one does. Does that kind of make sense? A little bit? Okay, so this is what's called a comparison test. These types of questions that we're going to go over, they're not necessarily asking us to determine what it converges to, like what is the numbered value from the integral. They just want a specific like yes or no answer. Does it converge? Do you have a finite area? Or does it diverge? Do you have an infinite area? So they're like yes or no's. What I want you to do in this little open space over here, we're going to make a little diagram of what this comparison test actually says, and I hope it makes sense to us. We're going to be working with two equations that are continuous, so no holes, no jumps, no asymptotes, on some interval, and we specifically know that one equation is smaller than or equal to the other one. So graphically speaking, maybe we'll draw the f of x graph below, aka smaller, than the g of x graph. These are the types of graphs we've been looking at so far, right? The ones that kind of approach an asymptote towards 0. That's what we're going to be looking at for this for this concept too. Okay? So let me ask you this. If g of x, if you were to find all of the area under the g equation, and you knew that that was a finite area, okay, that it would equal some number in the end, what do you think f of x does? Do you think f of x has a finite area as well? Or would f of x have an infinite area? You kind of got a 50-50 shot. So if you added up all of the area under g of x, you would eventually equal some number. Meaning all of the area this way is getting insignificant. Like the more you add, the less it affects it. What do you think about the area for f of x? It's also what? Finite, right, because if the blue area is insignificant the further you go to the right, doesn't it make sense the red area is insignificant as well because it's even smaller? You see how f of x is below g of x? Does that make sense? So if we can determine that g of x converges, okay, that it eventually reaches a finite number, then we know f of x converges too, or also. So if the greater one converges, the smaller one converges. All right, I'm going to try to erase the area portion here. One of the drawbacks of dry erase markers, you kind of got to redraw what you did before. All right, so on the flip side, let's say that if we were to figure out the area underneath the f of x graph and it diverged, meaning the area was significant as you go to the right. You keep adding it and adding it and adding it, and your value gets larger and larger and larger. If the f of x is diverging, okay, an infinite area, what do you think the area under the g of x graph would do? Also diverges, right? If this smaller area is significant, doesn't it make sense if you keep adding, or for the g of x, which has a larger area, you're going to keep adding even larger values to the g of x area, so that's significant as well. So if the smaller function diverges, so does the larger. Do those two make sense? All right, let's talk about kind of the one that isn't mentioned. Or kind of the two that aren't mentioned. What if f of x converges? Okay, so all of that area is, or the further you go to the right, the area is insignificant. It's getting smaller and smaller and smaller. That you keep adding it, it's not changing in number. If you know the smaller one converges, does that tell you anything about the larger one? Do you notice how that's not necessarily a true, or not a true statement, but it doesn't really tell you much about it? Because if the smaller one converges, we don't really know much information about the larger one to determine, well, what about this difference area in here? What is that doing? Is that significant or not? So we only have two options here if we're comparing two different functions. If the larger one converges, so does the smaller. And if the smaller one diverges, so does the larger. Those are the only two comparisons that we know for sure are going to be true. Okay, so we got to be careful with those comparisons. So we're going to keep that in mind as we go through some of these examples. So for the first one, they're going to be nice to us and give us a comparison to use. We'll eventually have to think of one ourselves, which is a little tricky, but let's just go ahead and tackle this one. So they're telling us for sure that this function is somehow smaller than this one. So we know the smaller and the larger comparison. We're going to try to determine whether this integral converges or diverges. Do we get a number as the integral value, or do we get some type of infinity as the integral value? We are not really concerned with the number itself. Okay, we're just trying to figure out, does it converge? So if we're trying to figure out this one, that means we're going to have to somehow test this one. Does this one converge? Maybe that tells us something about this. Does this one diverge? Maybe that tells us something about this. Okay, we're going to have to test that integral. So let's go ahead and test the e to the negative x from 1 to infinity, like the other integral is stating. Can we work backwards from e to the negative x? Yes. What would you get? Good, Cameron? It's okay. Yeah? There's only 6 of you. Like, if you want to shout something out, that's fine. All right. So let's go ahead and think about our bounds. We could possibly turn this into a fraction because we have a negative exponent. And by doing so, we can then use our growth rates to help us determine what's happening if we were to think about plugging in infinity. So if you were to plug in that top bound, you would have negative 1 over a huge number, which is basically 0. Yep. And then we're going to subtract what we get when we plug in the lower bound, which would be negative 1 over e. So it looks like we get 1 over e, which is a number, right? Okay, so we know that this function converges. So what does that tell us about the other function? If the larger one converges, what does the smaller one do? Yeah, that converges as well. Okay, so notice how we're trying to answer some type of area value for this function, but we're using a different function to help us figure that out. Okay, so we'll say since e to the negative x converges, so does e to the negative x squared. Actually, we should be a little bit more specific, because didn't it say determine if the integral of that function converges? So we'll say since the integral of e to the negative x converges, so does the integral of e to the negative x squared. It's not asking us to figure out what it converges to, it's just asking us, does it converge? Do you equal some number in the end? Doing okay? Kind of? It's going to get a little tricky. Okay. Let's take a look at the next one. So notice how for this one, it doesn't give us the comparison to actually utilize. It's just asking us to determine if this integral converges or diverges. So this time it's up to us to figure out a simpler function to use to help us determine if it converges or diverges. So if you really thought about this, okay, notice how your integral is from pi to infinity. So we're always going off towards infinity somehow. Okay, we have that improper integral. If you were to plug in infinity into cosine, what would you get? Or can you describe what happens to a cosine graph the further you go to the right? Yeah.
It just oscillates.
It oscillates, right? You're trapped between, do you know the numbers? Yeah? 1 and -1, okay? So what's a little tricky is the further you go to the right for this area, if this one's oscillating between 1 and -1, you either have at most 3, right? 3 plus 1, or sorry, 2 plus 1, or 1. You'd have 2 minus 1 if this one's oscillating. So can we think of some function, perhaps, that resembles 3 over x, or maybe even 1 over x, to help us determine if this one is converging or diverging? Okay, let's make note of this one for a second. So this is trapped between 1 and -1. Have we looked at a function so far in this section that is similar to 3 over x? Or even 1 over x? Yeah.
Or is it just like the power function?
The power function, okay? Remember how we talked about the p-series, or the power function, 1 over x to some power, right? Specifically, this power down here is 1, okay? So let's go ahead and we'll compare to 1 over x. Now we have to determine, because this one's a little bit easier for us to use, is 1 over x smaller than or equal to this function, or larger than or equal to this function? So this 1 over x, is it acting like this middle piece or the ending piece? If this was somewhere between 1 over x and 3 over x, anything in between, do you think this one's the larger one or this one's the larger one? Can we compare fractions? Pick a number for x, anything you want. 1, okay? If you plugged in 1 for this x, you would have 1, right? If you plugged 1 in for this x, you would have 1. if you plugged 1 in for this x, you would have 3, right? This function is going to be anything between, if you plugged in 1, anything between 1 and 3. Whereas this function is only ever going to be 1, if you plug in 1. So which one's the larger of the two? If this can be anything between 1 and 3, and this is only ever going to be 1. You see it, Cameron? The top one, right? Because this could be 1, this could be 2, this could be 2.5. Do you see that? If you're not sure, okay, because I'm trying to do this without a calculator, but if you're not sure, pick any x value you want and plug it into this fraction, and then pick any x value you want and plug it into this fraction, as long as it's between perhaps pi and infinity, because that's our bounds. I know 1 isn't in there, but it's still working out. If you pick any number you want and plug it in here and plug it in here, you can determine which one's the larger of the two. So we know that 1 over x is the smaller one. Okay, it could be equal to, right? Because this could be 1 as well, which is okay. Alright, so we're trying to figure out this one, which means we're going to test this one. So if you were to test the integral from pi to infinity of 1 over x, do you think that converges or diverges? It is a p-series. It is a power function. Do you remember kind of the barrier values if a p-series converges or diverges? What is our power value? P is well, if you brought it up, it would be -1, but the way it's written here, it's 1, okay? And if the power value is 1, does it converge or diverge? It diverges, okay? All right, so simple power series. We're going to, like I said, we're going to get pretty good with identifying these. Remember we did some of these in the past just by identifying the power, whether it converges or diverges. If this pi was a 1, okay, and this converge, we could figure out what it converges to, okay, but it's not asking us for that in this case. So by a p-series, okay, we'll label it p-series, since the smaller one diverges, we tested it, what do we then know about the larger one? If the smaller area is significant, meaning the more you add, the larger your area value gets, what do you think about the larger function and its area? It's also divergent, okay? So we'll say since the integral of 1 over x diverges, so does the integral of 2 plus cosine x over x. All right, so what we're trying to do is we're trying to think of really simple functions to use, like e to the negative x in the top example, 1 over x in the bottom example, really simple ones, okay, to try to compare and figure out which one is larger of the two to set up that comparison. Let's go ahead and try the next one. So if you look at c, I don't feel like integrating that. If I look at that, I don't really see a technique to help me, like reverse power rule or use substitution or by parts, anything like that. So since this integral might not be easy for us to work backwards from, let's try to think of one to compare it to. That way we can simply determine if it converges or diverges. Do we equal an area or do we equal infinity? So what's a little tricky with this one is, you notice how we have 2 terms in the denominator, where in the last one we only had 1? Okay, in the last example we just used 1 over x as the comparison, but in this one we have to kind of test here. Are we going to use 1 over x, that simple p series, to help us? Or are we going to use 1 over e to the x? Okay, how do we know which one to use? So let's go ahead and test both, perhaps. All right, so let's go ahead and maybe think about this. Pick any number you want between 4 and infinity. 10, okay. If we were to plug in 10, think about it, okay, into the original, we would have 2 over 10 plus e to the 10. We have no idea what that number is. If you have a calculator, we could figure it out. What if we were to plug in 10 in for 1 over x? Of the two, which one do you think is larger? Can we think about how fractions work? Yeah. How do you know?
Because the e to the 10 would be a really big number because it's a 1 over 10.
Notice how this denominator will always be 10, but this denominator will be 10 plus something huge, right? So when you have a larger value in the denominator, that makes your number smaller. So in this case, this fraction is the larger one. So we can say that 2 over x plus e to the x is less than or equal to 1 over x. So if we're trying to figure out this one, that means we're going to test the 1 over x. Do we already know what the integral from 4 to infinity is going to do for 1 over x? 1 over x is a p series. The p-value is 1. Is it going to converge or diverge? Diverge. Okay. So if the larger one diverges, does that tell us anything about the smaller one? No. Okay, so inconclusive. Okay, unfortunately, that comparison we chose wasn't informational enough for us. Okay, so we'll kind of cross that one off the list, and let's go ahead and check the other one. If you were to perhaps use 10 again, okay, plugging in 10 into the original and 10 into your comparison, which one is the larger of the two? Yeah. The 1 over e to the x. Notice how you have a plus 10 in this one, which is making this denominator slightly larger than this one. Okay, so this one is still larger. All right, so if we're going to try to figure that one out, we have to test this one. Yeah?
You have both your inequalities in equations less than equal to both of those. Which one?
Right. This one's the larger of the two, right?
Yeah.
It could be equal for some.
Should the other one be the other way? Inequalities, like,
This one?
yeah.
No, because, oh wait, this one's the larger of the two, right?
Yeah, okay.
Sorry.
That's, just
Should go this way, right? All right. So if the oh, wait a second. Now, in the way I wrote this one, this is saying the smaller one. No, wait. I think that was right the first time, wasn't it?
so it's smaller than both of them.
It's smaller than both of them, yep. Because if you plug in 10, this is a larger denominator than this one, which would make this a smaller value than this one. So this function happens to be smaller than both of them. Okay? All right, let's go ahead and test this one. Have we already seen 1 over e to the x, aka e to the negative x? Did we already integrate that one before? Yeah, okay. So I know the bounds are different, but can we realize that if we were to integrate e to the negative x from 4 to infinity, this would equal some number? We saw that before. You could actually go through it, right? You could work backwards, you could plug in the bounds, you would eventually get a number. You could do it, but I'm just trying to show you guys that we've already done it, so maybe it's informational for us to know that we're going to get some number in the end. All right, so we know that this converges. We don't really care what number it converges to, we just know it's going to converge to some number. So in this case, if the larger one converges, does that tell us anything about the smaller? Doesn't it converge as well? Okay, so we'll say since the integral of 1 over e to the x converges, so does the integral of 2 over x plus e to the x. A little tricky. All right, I don't think I left you guys enough room there to do the next one. So if you have room on the previous page, like where we did example D or B, maybe we can work this one out towards the bottom, or you can find some space somewhere else to draw it. I'm going to work on a different piece of paper. Or maybe you can find room off to the side. That's up to you. Okay. Let's check this one out. So this one's very similar to the last one we did. Notice how we have 2 terms in the denominator, so we're going to try to figure out which or what to compare it to. What do you think we're going to list as our comparisons to test? Can we think of a simple function to use? 1 over x, yep. And we'll say if that one doesn't really work out for us, we'll try 1 over e to the negative x. Okay. So let's go ahead and try the first one. We have to try to think about which one is larger. So try to pick a number between 4 and infinity and think about plugging it in for x, as well as this one. Maybe you want to do 10 again? Okay. So this would be 10 minus e to the negative 10th. What do you think?
So the 2 over x minus e to the negative x is bigger.
How do you know?
Because you're always taking 10 and subtracting, so it's going to be smaller.
Right, so you're taking 10 and you're subtracting something, right, which is making the denominator a larger number than 10, whereas this one's always going to be 10. So a smaller denominator is signifying a larger value, right? So we're going to go ahead and say that this is the larger one. And we'll check out what happens with that tomorrow. Okay, I know this is kind of iffy, okay, but we're going to eventually get more into this in the next unit, so it's going to start to sink in. For now, this is just a way for us to compare functions to help determine convergence and divergence.